Hi and welcome to Unit 2, Topic 2, Video 1. And in this video we're going to be starting to review trig functions. The topic is the trigonometry topic of Unit 2. So the end goal for this topic will be heading towards you looking at trigonometric identities and proving things with those identities and using those identities. But we're going to start with a review of trig functions first. And a lot of stuff here you've already done in methods. So you might fancy skipping over these videos, or you might just go through them quickly to make sure that you have these skills. Okay, so learning goals and success criteria as usual, and here we go. Let's first talk about radians. So hopefully you recall what a radian is. It's an alternate measure to degrees. Now degrees are nice, they come in the form of a package of 360, which is great. 360 is highly divisible and really useful. But the 360 itself doesn't really have a foundational reason for being there. A radian, on the other hand, does have a foundational reason for being there, because if we take our unit circle, which we're going to spend a lot of time dealing with our unit circle in these videos, our unit circle here has a circumference from start to finish of 2 pi. So what we're saying is that there's 2 pi radians in a circle, and it's a direct link between the angle that a circle subtends and then the circumference of that given circle. So a radian represents how far around the circumference you've gone, and it measures from 0 to 2 pi. That's why we use radians. Now, I've done that very quickly, so further reading on that if you'd like to, but in all honesty, you don't really need to know necessarily where it comes from to be successful in specialist maths. What you do need to know is that pi radians is equal to 180 degrees. That's probably the most common ratio that you'll use and see, so make sure that you remember that. I deal with just pi radians as 180. Some people like the 2 pi as a whole circle, either or. Once you have the pi equals 180, you can get 1 radian is equal to 180 over pi degrees, or 1 degree is equal to pi over 180 radians. So you've got that conversion ratio there. So let's have a quick look at some examples. A, we're going to convert 70 degrees into radians. Well, our conversion is that 1 degree is equal to pi on 180 radians, so therefore 70 degrees is equal to 70 times pi on 180 radians. And we use R or C. Our graphics calculator actually uses R, but C comes up a lot as well. And I can simplify this down to 7 pi on 18 radians. Now, we do tend, where we can, to leave it as in fractional form, exact form with a pi in it. But obviously we can't always do that. So occasionally you'll need to revert back to a decimal form. Just try and hold your accuracy if you can. B, we've got 2 pi on 5 radians. So we have 2 pi on 5, and we multiply that by 180 over pi to turn it into a degree measure. And then we can do some cancelling. That's 36. Pi and pi cancel out, and we're actually left with 72 degrees. So there's our answer to the second one. Just a bit of simplifying there. Practice that skill if you need to. And then C, which is easier but trickier at the same time, 2.73 radians. We still multiply by 180 on pi, but this time 2.73 is not going to give us a nice, easy pi's cancel out fraction that we can deal with. So we typically here just accept that we're going to need to move to a decimal form, which is 156.42. Now, in terms of estimating, it's always good to recognise that pi over here, radians, is 180. 2.73 is pretty close to pi. Pi is 3.14. So we're going to expect an answer that's pretty close to 180 degrees, but not quite there. So you should always be considering estimating your results as you go as well. So there's our start. Let's talk about our second thing you've learned in methods recently, and that's the unit circle. Now, I love the unit circle. It leads to a lot of things. I've got a bit of a summary here already, so I'm not going to have to do a lot of drawing. I'm going to do a lot of talking though. So here's our unit circle. The special thing about a unit circle is it's drawn on our Cartesian plane, x and y axes here, and it's drawn such that it has a radius of 1. So that's why it's called the unit circle. Now, in the unit circle, we have this orange height, which is length y, because y is there of our coordinate, and we have this green x, which is length x, because that's our x coordinate, whatever that is. And if we do the calculation sine theta, we get y over 1, opposite over hypotenuse. Therefore, y is equal to sine theta. So the height inside a unit circle is equal to sine of theta, the angle subtended from the positive x-axis. The distance across x equals cos theta in green, so that's the distance from the y-axis, that's measured by x, the x-coordinate, for the same reason, because cos theta is adjacent over hypotenuse. So we've got these beautiful ratios that come out. And inside this triangle, we've got a length 1, sine theta, and cos theta. And it leads, for a couple of reasons, to these two. So the first one is sine squared plus cos squared equals 1. And you should have probably seen this identity before. It's called the Pythagorean identity, and we're going to use it a lot in this topic. It comes from Pythagoras' theorem within this right angled triangle here. Cos squared plus sine squared equals 1 squared, and 1 squared is obviously 1. The other thing we can get is that theta is also has a tan ratio attached to it. Tan theta equals opposite over hypotenuse, which is y over x, but also sine over cos. So we have this second trig identity to do with tan. Tan is directly related to sine and cos in the way stated there. Now, the other thing that you'll need to be aware of and know is the cast diagram, and you'll need to be able to use the cast diagram. So the cast diagram gives us an indication of which ratios are positive and where. Because as you can see, let's start with the sine ratio. Sine is equivalent to the y value here, and so sine represents the height, and the height is positive above the x-axis and negative below. That means that the height is positive in this quadrant and this quadrant, but negative in the other two quadrants. Hence, within the cast diagram, we've got A for all and S for sine being positive. And the green one here is x, which is our cos theta. Cos theta is positive on the right-hand side and negative on the left-hand side of the y-axis. Hence, we have positive here and positive here. And of course, we also have tan theta is sine over cos. So in this quadrant here and this quadrant here, that's quadrant 2 and 4, tan is made up of a negative divided by a positive, or vice versa, and so tan is negative itself. But tan is positive in the first quadrant and also positive in the third quadrant, because sine over cos is negative divided by negative, hence it becomes positive. So some really nice reciprocal relationships there. It's just a beautiful thing to work with. Anyway, that's a summary, and you might wish to make some notes from that. Our graphs of sine and cosine are also important, and you should be aware of them. So our graphs repeat every 2 pi, and so you can see here this, so that bounced around a bit. This purple graph has gone up and down and that. Sine starts from the origin, whereas cos, which is in light blue, starts at a peak and finishes at a peak, and you should be pretty well aware of those. So just make sure that you've reviewed and you understand the sine and cosine graphs in particular. We'll cover some work on the tan graphs a little bit later in this topic. And of course, exact values you should be aware of as well. So I've got some notes here, quite a few notes, and so I'm sorry if it's a bit clumpy, but we have 9 exact values, and I'll highlight them now. The first 6 come from an equilateral triangle, and we just randomly give it side lengths 2 for a very good reason, because then when we drop that vertical line here, we get a side length 1, 2, and Pythagoras tells us that's root 3, and we can use this triangle to get sine, cos, and tan of 60, and sine, cos, and tan of 30, and we get all these exact values in this box here. There's 6 of them, and the other 3 come from our isosceles triangle with side lengths 1. Pythagoras tells us it's got a hypotenuse of root 2, and we can get the 45s there as well. Now, we also know the 90s and the zeros, so keep that in mind. Sine, cos, and tan of 90 and 0, we're well aware of and we can use. Now, I've got some notes. The first note is that we can rationalise the denominator, and we should aim to. I'm pretty bad at remembering to do that for this particular case, but it's always nice not to have a surd in the denominator. We also have a reflective quality in note 2 there. Sine 30 equals cos 60, and sine 60 equals cos, I should say 30, equals cos 30, and we also have that 45-45. These are complementary relationships. Sine theta is equal to cos 90 minus theta in all cases. And if you want more detail on that, just go back and have a look at the graphs. You can see a beautiful reflective relationship just happening here, where this and this match and they add to 90. I'll leave you with that to play with it. We'll often be using radians, so don't forget those major, more significant radiant conversions. And there's our cos sine tan of theta, cos sine tan of 90. Okay, and we also need to talk about symmetry in trigonometry because this is important, but you will have done a lot of questions on symmetry, so it's really worth going back and practicing some of these skills. So symmetry in trig says that sine is positive in the first and second quadrant, so sine theta is equal to sine of pi minus theta, and that's equal to negative in the third quadrant and negative in the fourth quadrant. And there's our symmetry. You can see in orange I've shown why that works and the heights that are occurring. We've got the same results with cosine, and we've got the same results with tan, but the negatives are obviously in different quadrants. But honestly, some textbooks and some people will tell you to memorize these things. I'm telling you, don't worry about it. Use the CAST rule. It works every time. Okay, so I'm going to leave it there. In our next video, we're going to talk about solving trig equations and running through that process. But for now, that's a lot of revision. It's a couple of weeks worth of work in math methods. So hopefully you've got some time to go back and review this because it is a basic skills understanding that you'll require for the upcoming specialist topic. All the best.